Yes, so I'm Kate Cevora. I don't need to read the title, it's quite long. Thanks for the introduction. I'll go quite quickly over the background as well, so that we talked about domain shift. But basically, it's a shift between data that's come from sources, and I think it's quite a big issue in medical image analysis because the data sets tend to be quite small, and there are a lot of factors that affect the appearance of an image. So we kind of split these up into a sort of basic causal diagram. We've got patient characteristics. So these are things like age, BMI, medical history that directly affect the patient anatomy. And then you have another group of kind of acquisition conditions that affect the appearance of the medical image itself. So things like the modality you're using, type of scanner, even the scan operator can affect the appearance of the image. And then finally, if we're talking about segmentation, which we are in this case, and you want to have a ground truth segmentation to train a model, the annotator that labels that segmentation will have some idiosyncrasies and potentially biases, which will affect the segmentation. So we're going to focus on this first group of characteristics here, patient characteristics. And the kind of sub-problem, which is called population shift. So this is when we have a shift in the performance, a shift in the distribution of patient characteristics, maybe between a training and test group. And that can lead to worse performance for certain groups, as has been proven a number of times for a number of different characteristics. And that's particularly the problem when these groups have been defined by some protective or sensitive characteristics like age, sex, or ethnicity. So our work was to undertake the first study to measure the impact of population shift across age and sex for abdominal species segmentation. So there has been quite a lot of work done already to look at the impacts of population shift in other modalities and anatomical regions. So I think particularly chest CT and X-ray have got quite a lot of attention. But the link between the population characteristics and the medical image appearance is going to be different for every anatomical region and modality. So we need to treat them separately. And we also wanted to compare this impact, this population shift impact, to the impact of a cross-data set shift as a kind of benchmark, because this is a very common and considered quite severe form of domain shift. So we use two large abdominal data sets, AMOS segmentator, you might be familiar with them. The main reason for choosing these is that they are one of few CT abdominal data sets to come with labeled patient characteristics. So we use these characteristics to create groups that are defined by age and sex. So we have under 50s, over 70s, and male and female. And then we use these groups to train an unit model to segment for abdominal organs. And we are essentially switching the training and testing groups according to these demographic groups we define. So we need some way of quantifying what happens when we change the distribution of the training population or impact on the test there. So we use a metric that we've defined called performance gap. And I'm going to talk about it in terms of, let's say that you have two groups. Group one is males, group two is females. Kind of illustrates it better. So we're interested in the performance gap for males. So we take the model performance. This could be DICE or Household 95 segmentation for males. And we have evaluated this with a model that's been trained on females only. And we subtract the same performance measure for males, but evaluated with a model that's been trained on only males. And then we average this performance. So in this particular case with DICE, we would expect normally to see a negative value for the performance gap, because we would assume that if a population is not represented in the training data, a model will perform worse compared to if they were represented. Although that's not quite what we found. We did see that the impact of population shift is significant, particularly kidney segmentation. So it's just I've just taken snippets of our results here at the time. But if it's a coloured cell, that means that we had a significant performance gap. Red indicates negative and green indicates positive. So you can see for the kidneys in the total segmented data set, we saw that the male group had worse performance when we trained the female model, about 6% difference, so quite a lot. But more interestingly, perhaps, we saw that across kind of a number of scenarios, proportionately representing a group in the training data did not ensure the best performance at test time. So to give an example, for females from the AMOS data set, we actually saw better performance on a test group when we trained with a completely male training set compared to a completely female training set. So that's quite counterintuitive with how we commonly think about how these kind of performance disparities arise. We also saw a lot of asymmetry between subgroups. So some kind of complementary subgroups where you saw that one would have a performance gap and the other wouldn't. And we were trying to figure out what might be a better explanation of the performance gaps we have seen than just the demographic labels assigned to the groups. And the idea of data set diversity came up. And unfortunately, in this particular study, we only had time to kind of look at one aspect of that, which was the standard deviation for organ volumes in the training data set. But when we just did a kind of rough look at whether the volume standard deviation correlated with the test time performance, we saw generally quite strong correlations. So that's really interesting. And it's kind of led on to my next piece of work. Yes. Oh, 1 minute, okay. So in conclusion, we saw that population matching the training test populations isn't necessarily the best way to achieve fairness for abdominal organ segmentation. And I think that means we definitely need a better understanding of data set diversity in terms of features that are actually in the images rather than demographic labels that are assigned to them. So in terms of future directions, I think we need to develop some more methods to measure data set diversity, particularly probably tailored to medical images. And we need some work to study the relationship between any diversity metrics we've got for images and the kind of downstream task performance. And this all needs, I think, to be tailored to medical images specifically. So thanks very much. That's all, and I'm happy to take questions.
Okay, we thought maybe everybody's performance was better when we trained on there. Because maybe, so for Alzheimer's, women are typically diagnosed a bit later. The theory is that they're better at speaking and therefore camouflage later. And their hypothesis was that it was just an easier learning task because the groups were somehow further apart. I don't know if that's true, but I was wondering whether you found some sort of early evidence that it is about diversity.
It was really based just on observation at first. So when I was creating training and test sets, I recorded a lot of different kind of metrics. So one of those things was organ volume, and it just became obvious that particularly for kidneys, the males had quite a much wider spread of organ volumes than females. So that became like an obvious thing to look at as a first step. And in doing that, I kind of realized that it would be great to have some more complete metrics for measuring diversity from image features. And I found that those are in quite short supply. So I'm currently looking at that now. How can we describe these images?